Minasan, konnichiwa, Zamurai Engineer desu. In this video, we will compare the three methods that we discussed, and we have an example of those methods are FDD, BDD, and CDD. What do you mean by this? That is forward difference, forward divided difference, backward divided difference, and central divided difference. So let's look at the result from the three different approximation methods. We have table to summarize the examples. So the three examples that we have given for chapter 2. Okay, we have the computation of acceleration at 16 seconds. Okay, we have the result, and we have the column for absolute relative true error. Okay, so what can you say about that? We cannot immediately say that the forward and backward are better than the other, but also for the central, we cannot immediately say these things. No, in this particular example, the result gives us, and we can make a conclusion that in this particular example, central divided difference, CDD, is the best method. Okay, because we only have what? 0.07% error. Okay, very small. 7 pesos for every 10,000. For every 10,000 pesos, you only lost 7 pesos. That is negligible, no? 10,000 pesos, 7 pesos. Okay, that is negligible. Okay, and again, finding the value of derivative within a pre-specified tolerance. In real life, because we have pre-specified tolerance, what is the tolerance? 2 seconds in our examples. But in real life, one would not know the exact value of the derivative. So one how to know how accurately they have found the value of the derivative? A simple way would be to start with a step size and keep on having the step size and keep on having the step size continuously until the absolute relative approximate error is within a pre-specified tolerance. Okay. Having the step size. The step size is delta t or delta x. That is the step size. So if your error is not yet within the tolerance, so make the step size smaller, or in this case, they recommended make it half. So 2 seconds, make it 1 second. That is half of 2 seconds. If still not yet within the tolerance, 1 second divided 2 is 0.5 seconds. And so on, until it is within the tolerance. Okay, so take the example of finding the first derivative of b for the given equation, as we are using this problem repeatedly at time is equal to 16 seconds using the backward divided difference scheme. Let us do this. Okay. Okay. Let's do this for different what? For different step size. So first, our step size is 2 seconds, as you can see from the first column of the table. Okay, 2 seconds. So we are what? Going to find from our previous example, our answer is what? 28.915. Okay. If make the step size smaller, okay, smaller and smaller, we can get smaller and smaller value of error. This is the value of error. But the value that we want to know is going nearer and nearer to the actual value. Going nearer and nearer to the true value. Okay? What is the true value of our required acceleration at 16 seconds? That is 29.674. That is the true value. And look, using the backward divided difference, very small error. Okay. 1 second step size, we only got 1.3% error. 0.5 seconds, we already get an error less than 1%. 0.25, we get an error less than 0.5%. And 0.125 seconds, step size, we get an error that is less than 0.2%. Imagine that. Very small amount of error. Do these things, confirm this table, use our previous video as a pattern, use our example as a pattern, and try to do each and every one of these. What do you mean by each and every one? Use delta T 1 second here. Okay. Confirm this result. Find the absolute true error. Again, another example, another practice. Make delta T is equal to 0.5. Another one, make delta T as 0.25 in another 0.25. And confirm this absolute relative true error. Okay? That's how you get your practice. You will do it yourself. Okay? Just recall, review, rewatch our lecture videos, and use those lecture as a format, our example as a format, in order to solve this assignment, another assignment, another practice assignment. So find the value of the derivative within the prescribed tolerance value. Okay. From the above table, one can see that absolute relative approximate error decreases as the step size is reduced. At delta T is equal to 0.125, the absolute relative approximate error is just less than 2%, meaning that at least 2 significant digits are correct in the answer. Okay? 2%. Okay? At least 2 significant digits. Okay? So, that is minimum. That is at least 2 significant digits are correct in the answer, meaning what? What is the answer? The answer is what? What is the answer? 29. So the value 29 is correct. The value 29 is correct as a minimum. Actually, the third significant digit is also correct, 29.6. 0.6 is also correct. Okay, but the 2 significant digits is sure to be correct. The value 29 is sure to be correct. Okay? Imagine that. We can analyze it that way, that we are sure enough. Yes, we are sure enough. Okay? Okay. Finite difference approximation of higher derivative. What about for higher derivative? One can use Taylor series to approximate a higher order derivative For example, to approximate the second derivative, the Taylor series. Use the same sequence of derivation, but now you are what? Trying to find out the second derivative. And because it is second derivative, we may need what? More terms. More terms. Okay, so because this is second derivative, we may need those. Okay, so in this derivation, this is the second derivative. So we are looking at this. So we can use this transposition so that we can have what? Simpler equation. This is Taylor series. So let us find the equation for this one. That equation is this one. So we need what? 1, 2, 3. We need 3 terms rather than 2 terms because we are looking at second derivative. Okay, we need 3 terms. But now our denominator is delta x squared. Take note, we are now second derivative. So we can do the other higher derivatives. Just follow this procedure. Okay. So, for example, number 4, the velocity of a rocket is given by the same function that we are always using. Use forward difference approximation or FDD of the second derivative. Okay, of second derivative of the velocity to calculate the jerk. So we are not interested in finding the acceleration anymore because acceleration is first derivative of velocity. What is the second derivative of velocity? That is what we call jerk. From our physics, recall our physics. Recall physics with calculus. Physics for engineers. Okay, physics for engineers, we have what? The second derivative of velocity is what we call jerk. Okay. Jerk. What is the jerk at t is equal to 16? Use step size of 2 seconds. So again, we can use, but now we want to deal with second derivative. So let us jerk function of t. Okay, jerk function of t. We already know that this approximation is equal to this one. There are 3 terms. That is velocity at t I plus 2 minus 2 velocity of function time t plus 1 plus v of ti. So divided by delta t squared. So we need to find out what is ti plus 2, what is ti plus 1, and what is ti. Ti is 16. Okay, delta 2 is 2. And therefore, ti plus 1 is t plus delta t, that is 18. What about ti plus 2? That is ti plus 2 delta t, that is 16 plus 2 times 2, that is 18 plus 2, that is 20. And therefore, we have the following equation or approximation. This is forward approximation. This forward approximation. So we have what? We know that this is forward for second derivative because the important target x value is 16 and the other important domains are 18 and 20. That is a forward number from 16. Okay? That's why we know it. So we need velocity at 20 and velocity at 18. Of course, we already know the velocity at 16 from the previous example. So what is our velocity at 20? Use the same equation, just replace the variable t by 20 and we can find out the answer. We already know the velocity at 18 because this is the same example. We have the same answer. For velocity of 18, which is equal to 453.02. And also, we already know the velocity at 60. Okay, so using the values calculated in this page, we can now find the jerk at 16. What is the value of the jerk at 16? That is, substituting those values, we have 0.8451 meter per second cube. Okay, meter per second cube, that is jerk. Okay. Okay. The exact value of jerk at 16 can be calculated by differentiating the given function twice. First derivative, then second derivative. Take the second derivative of the given velocity function. And that is very simple matter for you because you already successfully passed calculus. Okay. First derivative, then second derivative. This is the equation for the first derivative, as we already know from the previous modules. How about the second derivative? Take the second derivative of that. We can do it and simplify. We can simplify it to this point. Okay. Okay. So after we simplify it to this point, just replace the value 16 as the value of the variable t. Okay. So, and we can find out that the true value is 0.77909. Okay. So absolute relative true error is what? 8%. So this is on the acceptable and not acceptable because this is more than 5%. More than 5%. And as an engineer, I am actually using 3%. Mathematicians, statisticians, they are using 5%. Those are acceptable level. But me personally, I'm using 3%. Okay? So this is 8%. This is more error. So I cannot accept this as personal opinion. No. So, but anyway, that is the example. How to make this error smaller? The same thing. Use smaller step size. So our step size is 2 seconds. Make it 1 second. Not yet less than 5%. Make it smaller again until it gives us the absolute relative true error, which is less than our tolerance value. Okay. My tolerance value as an engineer is 3%. Okay. What about you? You can set your own tolerance level. But generally, conventionally, 5% is acceptable. In mathematics, in statistics, 5%. Okay. So that is our example number 4. Accuracy of higher order derivatives of approximation. The formula given by equation 5 is forward difference approximation of the second derivative and as the error of the order delta x. Can we get a formula that has better accuracy? Yes, of course. You can get the central difference approximation of the second derivative. We can even have, because we are using one. First, forward, we can also use backward, and we can use central difference. Okay. So if you use that, let us see if we can have a smaller error. Okay. The same equation, use the central difference this time. Okay. Take note of the formula using the central difference. Okay. This is the formula for the central difference. Fxi plus 1 minus 2 fxi plus fxi minus 1 divide by delta x squared. Okay. Let us use that. And then the same given by the problem. Solution. We need to calculate the values for B18, B16, and B14. Okay. So we already know that from the previous example, and divided by 2 squared. So delta x is 2. So we can find the jerk by first finding out the value of B18, B16, and B14 from the previous example. Just substitute. The jerk is 0.77969. And so we'll notice the error. Solve for the absolute relative true error. Okay. Okay. You'll notice that the absolute relative error is less than 0.1%. Actually, that is 0.08%. What is 0.08%? That is 8 pesos for every 10,000. Very small value, negligible value. Negligible because if your neighbor won 10,000 in a lottery and give you a tip of 8 pesos, you are not happy about that. Even though you are just what? Receiving a blessing, you are still not happy about that because you know 8 pesos out of 10,000 is negligible. Please be true to yourself. You know that you are not happy with that. No? He won a lottery for 10,000 and he just gave you 8 pesos. Not even 100 pesos. Okay? You are expecting at least 100 pesos. Okay? So, what is 100 pesos of 10,000? That is 1%. Okay? So, imagine that this error is too small. Okay? And this is our last slide. Thank you for listening. Again, this is Dr. EYPEI, Preaching Engineering for Nation Building.